Well, today is going to be pretty easy, really, because we're just going to compose transformations that we're already familiar with. What do I mean by compose? It means just put them together. In other words, apply successive transformations. And it's kind of obvious that would be an okay thing to do. After all, suppose we applied this translation transformation to A, and it shifts it over to here, and then we reflect it about the x-axis. Well, this object right here happens to be the result of a transformation. But how do we know that? If we don't look at this, now this part here doesn't exist. Well, fine. We have an object here, in this case a triangle, which we reflect. The fact that it came from some other transformation seems kind of irrelevant. And in fact, it is irrelevant. We could have applied 15 transformations in order to arrive at this triangle at this point. There's absolutely nothing stopping us from applying one more transformation. So we can compose as many transformations as we want, of as many types as we want. The one that I showed before I split it up, let me try that, see if I can put it back. Like magic, it's right back. This object could have come from some other transformation. How do we know? Anytime you see an object, that object could be the result of 15 transformations. There's no way to know. When you look at an object, for instance, look at this triangle here. It tells you absolutely nothing about the history of that triangle, how we arrived at this triangle. All we know is this triangle is in this position at this time. It could have been translated 100 times before it wound up here. There's no limit to the number of transformations you can apply in succession, or compose, as they say here. This particular transformation, where we slide one way and then reflect, they gave it a special name. It's called a glide reflection. No particular reason that I know of. That's just what it's called. And it's only a special case of transformation composition. In other words, composing two or more transformations together. What else can we say? Well, notice that we used a translation, which is an isometry, a congruence transformation. I like rigid motion myself because it implies that nothing changes, and that's good because the lengths and the angles don't change. So from A to A prime is congruent to A. Here we have a reflection, which is also an isometry. A prime is congruent to A double prime. So, the composition of isometries or congruent transformations or rigid transformations is, again, an isometry or a congruent transformation or a rigid transformation. In other words, if I compose rigid transformations, I could put as many of them together as I want, and I still end up with a rigid transformation. Why? Well, it comes straight from the transitivity of congruence. A is congruent to A prime is congruent to A double prime. We can use transitivity and cut out the middleman and say that A double prime is congruent to A. Real simple. But of course we have a couple of theorems about composition of two transformations. They have to do with reflections about lines. Suppose I reflect an object twice. about two parallel lines. Here we have the line x equals -5, and I reflect this rectangle, and I get this. Notice this line here, this is the reflection of this line, and this is the reflection of this line. It looks like I just moved it over, but I didn't. That's why I made these two sides different colors. If you shift this over, you don't get the same polygon. You have to actually reflect it. This side flips all the way over to here, and this side goes to here. In a translation, everything moves the same distance, but you can see that, let's see here, 1, 2, 3. This line here moved 8 units to the right, whereas this line moved 2. So there's definitely not a translation going on here. What about when I reflect this one about this line? Same thing, it's not a translation. This line goes over here, and this far line ends up in this far line over here. Well, wait a minute. Now that I've reflected these twice, it's kind of like I flipped this, isn't it? Well, if I flip it, and then flip it again, I end up right back where I started. Well, except that this object is shifted, just like in a translation, isn't it? And in fact, two reflections about parallel lines will always result in a translation. In other words, we get the original object back in its original orientation, which makes sense. We've got the original object right here, but different orientation. Here, it's back oriented the way it started, but it's shifted over quite a bit, which is just a translation. So, what we have here is that two reflections together is the same as just one reflection. After all, this went from, say, -8 to 1. That's a change of 9. So our displacement vector is 9, 0. That would be the translation vector. You could write that AB goes to A plus 9B. I don't know if that's very easy to read, but I think you know what this means here. We apply a translation vector to the components. We get A plus 9 and B. What if these lines aren't parallel? What happens then? Well, here's where I reflected polygon about the line x equals -4. And I made every side a different color so we can keep track of what's going on here. Because they have something called symmetry in a rectangle, which means I can flip it in a lot of different ways, and it still looks like the same rectangle. You can't really tell that we've done anything. But if you make them different colors, or conversely, you can actually label the vertices A, B, C, D, and then see where, if this were A, then A prime would be over here. Colors are kind of graphic. So we reflect it and get this, just like we did before. But now we reflect it again about the x-axis. And we get this. So we started over here with this, with the red side up on top. After two reflections, the red side's on the bottom. The blue side was on the left. After two reflections, the blue side's on the right. And if we take a look at what happened to corresponding coordinates, for instance, let's check out where the reddish brown hits the yellow. That's -7, 3. Well, what's that point here? Well, unfortunately, we can't use our coordinate rules for rotating about the origin because we're not rotating about the origin. But graphically, the same thing holds. For instance, if I take a line from here to here, and another line from this point, and this point is where the two, remember this is our second rotation line. And what I'm getting at here is that when we perform these two reflections, our final image is exactly the same as if we had taken this and rotated it about this point here. In this case, it would be 180 degrees. Why? Well, if you were to draw a line from this point out to here and rotate it until it met up right here, you would have rotated 180 degrees. And it's kind of easy to see how that works. For instance, if we take this line from the point of intersection out to where the reddish brown intersects the blue, well, that's exactly the same distance to here. The same line matches up from the point of intersection, that's this point here, back to this corner. If we call this A, that goes over to A prime here, and A double prime down here, which is just, you can see it's a 180 degree reflection, just like what we did in the previous section. For instance, I could extend this line, and you can see this is just a straight line that goes from here to here, which is the equivalent of a 180 degree reflection. In this case, we wound up with 180 because of the angle formed by the two lines of reflection. In this case, it's a 90 degree angle. The resultant rotation is double the acute or right angle, in other words, the smaller angle, formed when your two reflection lines intersect. Since these lines intersect at 90 degree angles, we've created a 180 degree rotation. If this line, if we were reflecting this about, say, a 45 degree line, in other words, we intersected this line here at 45 degrees and then reflected it, well, that would be like a 90 degree rotation about the point of intersection. That's the most important thing to remember, is that when you perform two reflections, if the lines are parallel, then it's just a translation. If they're not parallel, then it's a rotation about the point where the two reflection lines intersect, and the angle of rotation is just double the angle of the intersection of these two lines. If these two lines intersect at a 45 degree angle, then your double reflection will be the equivalent of a 90 degree rotation, etc. If they intersected at 30, then your rotation would be, your double reflection would be the same as a rotation about this point of 60 degrees. Now, they want us to glide the line, in other words, translate it, and then reflect it. It's pretty easy, really. Start out, just graph the line. We've got the point 2 minus 5 here, and 4, 0 here. Pretty easy. Now, the translation. We just drop it down 1. 4, 0 goes into 4 minus 1. 2 minus 5 becomes 2 minus 6. Now, if we reflect it about the y-axis, 4 minus 1 becomes minus 4 minus 1. 2 minus 6 becomes minus 2 minus 6. Remember our coordinate rules. If we're going to reflect about the y-axis, all we do is change the sign of the x-coordinate. Real easy. So this is the result of our composition. Performed 2 transformations and wound up here. Well, with this, our mission is to figure out what composition of transformations. You could probably call them a combination of transformations also, I suppose. What's in a name, eh? Well, in mathematics, a lot of things are in a name. This looks like a translation, right? It looks like we took a down 1 and over, what, 1, 2, 3, about 6, maybe? And each of these did the same thing. So this part's pretty easy. This, almost looks like a reflection, but not quite. Notice it's reversed. A reflection would have this long side right here. This one doesn't. But if we were to rotate this 180 degrees about the origin, this would end up right back here, I think. We double check that. That might not be a 180 rotation. Oh, I see what's going on here. Looks more like a 90-degree rotation, doesn't it? It goes from this quadrant to this quadrant. 180 would have put us over here. This swings down. So let's draw it in, just to... Yeah, looks like a 90-degree rotation to me. But we can check it. What's our first translation? We probably ought to write that one down first. First, we have that xy, and this is a translation which goes 1, 2, 3, oh, only 5 units to the left. Okay, so that's minus 5, and it goes down 1. So our first translation is minus 5, 1, or we could write it this way. That's our translation. How do we know this is 90 degrees? Well, let's take a look here. This is 1, 2, 3, 4, and this is 2. So this is the point minus 4, 2. This is the point minus 1. Minus 4. Well, I hope you were screaming at me. I just made a terrible mistake. An awful mistake. An inexcusable mistake. I treated this as the pre-image, this as the next image, and then this as, this is the pre-image, this is the image, and this is the next image. Well, that's wrong. You can tell from the way it's labeled. This is the pre-image. This is the image under what looks like a translation, of course, just like it was before, but it's a different translation. I thought we were going from here to here. Don't ask me why I thought that. It's totally obvious, and you probably recognize that this is the pre-image, and we're going from here to here. Yes, I'm sure you knew that. I'm the only one here who is confused. But watching stupid people get confused can be very instructive, so keep watching me get confused and you'll fly right through your state exam. The translation that takes us from here to here is pretty close to what we had before. It's plus 5 because it's taken us to the right 5 units and up 1. So we could say our translation vector is 5, 1, or that xy goes to x plus 5 and y plus 1. If we look at it that way, our rotation becomes much simpler, I think. Let's take a look at A and A double prime. It looks to me, let's see if it's true. Well, come on. There we go. Yeah, going right through the origin is a straight line connecting A prime and A double prime. So this is a 180-degree rotation all the way around to here. Same thing here. Same thing here. It's one thing nice about 180-degree rotations. We can check the coordinates anyway, just to make sure. I was just going to say that 180-degree rotation is one of the few that's very easy to eyeball, because a straight line is a straight line. If there are no kinks in it or bends or anything, you could probably tell a straight line from one that's not. But what are the coordinates here? We get 1, 2, 3. 1, 3. Over here, -1, -3. And if you check your coordinate rules for a 180-degree rotation, you'll find this is it. You just negate the x and y coordinates. So this turned out to be a translation from here to here, and then a rotation about the origin. Well, here's where we use our double reflection theorem. Remember, I pointed out that if you reflected something twice about two parallel lines, that just becomes a translation. If you reflect it twice about lines that aren't parallel, that's the same as a rotation about the point of intersection, and the rotation is equal to double the angle of intersection. Well, this looks to me like one of those cases. This sure looks like a reflection. A prime looks like a reflection of A about this line here. On the other hand, A double prime is a reflection of A about this line here. They're not parallel. They intersect at 55 degrees. So A to A double prime is the same as a reflection, a rotation of 110 degrees. I went in ahead and drew in a couple of radii, and this, you can see 90 degrees would be about like that, so yeah, this looks like about 110, double the 55. So the answer was this whole angle here is 110 degrees. Well, okay. Looks like my favorite dim brothers, Inseam and Fleabite, have gotten into geometry once again. And they think that this is a glide reflection. And it almost is. What is our translation? Well, we shift everything this way. But then we reflect it about the y-axis. That's this here, right? Well, there's one thing about a glide reflection that this doesn't quite meet. If we shifted it straight up, it would be a glide reflection. In other words, shift it straight up and then reflect about the y-axis. That would work. Or if we shifted it this way and then reflected about a line like this, that could work. But the line, or vector, which represents our translation, has to be parallel to the line of reflection. Otherwise, it's not called a glide reflection. It's still a perfectly legitimate composition of transformations. It just doesn't fit the definition of glide. So don't forget that a glide reflection is a particular type of translation and reflection where the translation and reflection lines have to be parallel. The vector, which would represent your translation, has to be parallel to your line of reflection. Then you have that very special case, which we call a glide reflection. Otherwise, it's just a translation and a reflection. Well, here we're given the vertices of a triangle. First thing we have to do is rotate it 180 degrees. About the point -2, 2. Well, 180 is particularly easy because it's just a straight line, and it has to have the same length. So we go from here to here, for instance, and swing this around 180 degrees. Well, that just makes it a straight line. The question is, how far out do we go? Well, this radius has to be exactly the same length as this one. But we can do that without explicitly computing the length. How do we do that? Well, from here to here is 2 units up and 5 units over. So the length of this would be the square root of 2 squared plus 5 squared. But we don't need to worry about that. We just need to remember that it's 3 units up and 5 units to the left. So we have to do the same thing on the other side. Which one was I looking at here? This one here. Yes? Yes. It's 2 units up and 5 units to the left. So we go 2 units up, 5 units to the left, and end up right here. In other words, you can just match up the horizontal and vertical components in order to make sure that this radius from here to here is exactly the same length as this one from here to here. Same thing over here. It's got to be on this straight line here somewhere, but where? Well, we have to go, to get to here, we go over and up a whole bunch. Do the same thing here. So this is like over 3, over 3, and here we went up from -3 to 2, that's 5, and from 2 to 7, that's 5 units. So here we have the image after rotating it 180 degrees. Now we're going to reflect this about the line y = -x. And that's easy because we get a nice simple rule for that. Remember, it's, I write it right here, AB goes to -b minus a. And luckily, well, they said find the image, so I guess that means we can just list the coordinates and maybe graph it. Let's see, line y = -x is going to go through there, so this reflection is going to be way down here somewhere. If I can keep it on the page, I'll graph it, but we'll start out by just listing the coordinates. And they would be, well, this could make more sense if I go ahead and label these as J, L, and K, and then their images J prime, L prime, and K prime. Now we're going to find J double prime. That'll be the image of this, which is just going to be with the rule we have here, -7, that's -7, 5. And that's the image. That's J double prime. For K, we have -2, 6. Just applying this rule up here again. And that'll give us K double prime. All that's left is L, which is going to give us -4, 7, and that's L double prime. And this is kind of a mess, but I went ahead and drew in the reflection here. We got the coordinates over here. It's off the grid, of course. Here's our line, y equals -x. And we reflected this thing about this line, so naturally this corner of it. And since I'm off the grid, I guessed at where the points were, and you can see that my guess wasn't all that great, because this little section that's sticking above here, well, that should be exactly the same length and sticking out here. And then this section here corresponds to this here. You see, the line of reflection cuts right through the object, so there's not too much separation. You can see the overlap caused by that, creating a visual mess. But if your eyeballs can make sense out of this, this is your final image after reflecting about this line here, y equals -x. Well, that's about it.